In the second part of this lecture, I will speak about regularization methods. The purpose of regularization methods is generally to reduce the test error of a machine learning algorithm, or more generally reduce its generalization error. So it's usually not the goal to reduce the training error. In fact, we will often increase the training error if we use regularization, because regularization means we somehow restrict the expressiveness of the function that we are using to fit the data. But what we want to achieve is we want to do better on data that we did not train on. And often this has to do with increasing bias but reducing variance. Yeah, so we reduce expressiveness of the function we're using somehow, so that will increase generally the bias and therefore the training error, but it will reduce hopefully the variance of the estimator and therefore also reduce test error, or at least expected test error. Okay, and different examples of regularization methods is we penalize the range of parameter values. So that is used a lot in shallow learning methods such as regression or support vector machines. So for example, we can use L0, L1, L2 constraints that penalize basically the number of non-zero entries, the sum of all entries in a parameter vector, or the squared sum, the Euclidean norm of the parameter vector. But of course, we can also do this with neural networks, where L0 and L1 are somehow sparsity constraints, so they try to promote many weights that are 0 or close to 0, and L2 is known as weight decay in neural networks. Then we have data augmentation methods. So we increase the training set size by exploiting certain invariances that we want to be resistant against, such as rotational invariances or scaling or changes in lighting in images, for example. And then finally, we will speak about ensemble methods, where we combine multiple learning algorithms, multiple hypotheses that explain the training data in some way. So, as a first method, we will look at how can we avoid overfitting during the training iteration itself. So often what we observe is that if you look at the training loss or the training error, that it decreases over time. Well, that's what you should always observe, that there is generally a decrease until some plateau is achieved. And this plateau might not be at zero loss, but might be at some finite value, which is then essentially the bias. But the validation or test set loss, and usually we track the validation set loss during training, may reduce to some minimum and then increase again. And this increase can be more or less drastic. In this case, it's quite subtle, but you see there's general increase after about 30 or 40 epochs. And that basically means that the optimization method, the neural network training, in this case, is overfitting at some point. The training error still reduces after these 30 or 40 epochs, but the generalization error on the validation set does not. It gets actually worse. So in a way, we're optimizing too much. We are exploiting some structure that is in the training set, but not in the validation set. So we are at this point, we are not doing a good job in generalization anymore, even though the training error keeps reducing. So one thing we can simply do is to stop training here, to stop training at the point when the validation set loss starts increasing. And this method is called early stopping. And this is a frequently used regularization method. So we return the model with the minimal validation error that has been encountered during the training procedure instead of using the model with the minimal training error or the model at the end of our predefined number of epochs that we train. So in some sense, this is a hyperparameter selection algorithm where the hyperparameter is the number of training steps. And effectively, this restricts the training or the optimization procedure to a certain volume of parameter space around the starting point, and we can interpret this as some form of weight decay. If we stop training after the local minimum in validation error has been encountered, and for that we usually define something like a grace period. If our validation error keeps increasing for a certain number of steps, then we stop and then we take the minimum validation error model that has been encountered to this point. So then we can actually reduce training time quite a lot because we might end up doing many less epochs or training iterations than we were originally planning to. And this method is frequently used. It's very easy to use, very inexpensive, and is basically compatible with any learning problem. The next regularization technique I want to talk about is data augmentation. So data augmentation is making changes or modifications to your data set by augmenting it with certain transformations that you believe the learning problem should be independent to. So for example, let's say we have a classification problem and here's a butterfly that we want to be able to recognize. We should be able to see that this is a butterfly independent of whether it has less texture, if it has no color, so if it is a grayscale image instead of a color image, if it has stronger edges, if it has only edges, or if it's rotated or flipped, if it is scaled, bright, dark. So there are many modifications you can think of that after which you think you should still be able to see this as a butterfly. And you want to train your machine learning method to be robust against these changes. So what you can do is you can apply these changes to the training data points yourself and just introduce them as new data points with the same labels. And therefore, practically you have augmented or enhanced your data set in some sense. Now, this artificially increases your training data. These are in some sense fake samples that you introduce. They're not truly new data points. They're not independent. They've been derived from existing data points, but of course they do provide additional information with respect to what changes the learning problem or the learning method should be insensitive to. And examples you have seen on the slide before. You can add translated, rotated, scaled, etc. copies of your training images. Translation is often not needed. If you use convolutional neural networks, you have translation equivariance built into the convolutions. And then with a combination of convolutions, pooling, and classifier, in the end you have an approximately translation invariant classifier. Rotation can also be built in by using rotation equivariant convolutions. They exist. And in the same way, you can make up other types of convolutions that have invariance or equivariances with respect to certain symmetry groups, with respect to scaling, for example, or changes of lighting or other things. But there's always a balance between how much do you want to put into your convolution, so how much intelligence or hard wiring you want to put in there, and how much do you want to rely on data augmentation. Yeah, some symmetry groups, some transformations are effectively pretty large, and it's really hard to learn them just by data augmentation. Yeah, for example, consider that you're not working in 2D but in 3D, and then you look at rotations. There's just a lot of rotations that you can do in 3 dimensions. So you would have to sample this rotation space quite a lot. And if you really want to be rotation invariant in 3 dimensions, it's probably better to build that into your convolutional layers themselves. And the same is true for translation equivariance, because it's simple to do that in convolutional layers. But in some cases, it may just be difficult, conceptually difficult and computationally expensive to have certain equivariances in the convolution layers. And in that case, data augmentation could be a good solution because it's very easy to do. You have to be careful. Certain invariances are not with respect to the whole symmetry group. So for example, if we have MNIST, we do classification of handwritten digits and we have a 9, we rotate it by 180 degrees, then it's a 6. So the class has changed. So you're not invariant with respect to the full rotation. So what is an invariance depends on the specific learning problem. And another frequently used type of data augmentation is adding noise. So adding small amounts of noise to an image, let's say, should not affect a classification result. But neural networks are often quite sensitive to addition of a little bit of noise. And therefore it can be quite helpful to introduce some noise in the training procedure to make the classifier less sensitive against that.